Okay, all right, so let's talk about calculus. This is 11.1. And we want to introduce the idea of a limit. So this is just a kind of dipping your toe in the water as far as calculus. So when you guys go on to take calculus, you won't be totally in the dark. And so they use an example just to kind of get the idea of a limit in your mind on page 750. And they said, we're given a problem. It says you're given 24 inches of wire and you are asked to form a rectangle whose area is as large as possible. All right? How would you even tackle something like that? You just got some wire and I want to make a shape that's as big of an area as possible. What dimensions should the rectangle have? Any idea how you would tackle it?
No.
Yeah.
Would it matter?
Huh? It would, yeah. Yeah, and so as we're going to see in just a minute. So what they note is that this is the formula for the area of a rectangle. So we've got 24 inches of wire, right? So we know then that the length, the perimeter of the rectangle will be represented by this equation. Does everybody agree with that? Right? And so if we solve for L, we would get L equals 12 minus W, right? And then the area of the rectangle equals L times W. And so then we can just plug in that for L and get 12 minus W times W. And so that's going to equal 12W minus W squared, right? Sometimes it's W, sometimes it's W. It just depends on what I'm feeling like in the moment. You should hear my grandson say W. It's like, he says all the other letters of the alphabet pretty well, but it's like, O-U, or something like that.
Is W called a W because it's a W? It looks like a W.
I guess so. It's sort of more like a W. We should be required to always draw our
because like some people do
W's like that, right? Because it actually looks like a W.
Yeah, but some people do it like two V's almost, so like double V.
Well, I do that when I sign my name. I'm like that.
That's more like two V's, right?
I agree. Maybe we should have two letters in the English language depending on how you draw it. Have double V or double U. It's trying to make English even more confusing.
That's what I think we should do.
Than it already is. And so this is this is the equation. So we're trying to figure out if we base the value of L on W, then we can just draw one equation with W in it. There's the area equation with only the width represented. And so we can start plugging in values just sort of randomly. And they have a table where they did that, where they said if W is this, then the area is going to be this. And so they did their table horizontally. Just the rebel that I am, I'm going to draw mine vertically. You guys know how it is. So I know it, living on the edge. And so this is 35. And this, if we did 5.5 here, 35.75. And 5.9. They're just kind of showing you as you get closer, it looks like, everything's kind of increasing and getting closer and closer to 36, which is the value that we get whenever we plug in 6. Once we get above 6, if I do 6.1, now it starts getting smaller. Right? 6.5 is 35.75. So, to answer your question, Stephen, it won't be the same, right? It varies depending on which value that you pick. And it seems from just randomly picking some values here that 6 for the width is the biggest, will give us the biggest area, right? And so what we can say is that for that equation right there, that the limit as W approaches 6, that's what that means. The limit as W approaches 6 of the area is equal to, we'll rewrite it with the formula in there, the limit as W approaches 6 of 12W minus W squared. That's just what I wrote over there for the formula for the area. It's going to equal 36. So as we get closer, as we approach 6 from this direction, from numbers that are less than 6, it's approaching 36. As we approach 6 from the other direction, from numbers that are bigger than 6, all of them seem to converge on this point, which is an area of 36. Do you guys see that? So that's the way limits work. All right? you'll be looking at the limit as some variable is approaching a particular value, and you're kind of considering it from both directions. As we look at numbers that are smaller and numbers that are bigger, they will converge on the point that we refer to as the limit. Does that idea make sense to everybody? All right? Yes?
Yeah.
Everybody with me? Okay. All right, so we'll write down the definition of a limit, which is this. And it says if f of x becomes arbitrary, let's spell that right, arbitrary, that's an A, something that doesn't look right, arbitrarily close to a unique number, L, as x approaches C from either side, so whether it's a bigger number or a smaller number, then the limit of f of x, of that function, as x approaches C is L. The way that we would write that is the limit as x approaches C of f of x equals L. So that's both the definition and how you would write that down. All right, so let's try another one. Just kind of give you a little more practice with limits. And we're asked to find the limit as x approaches 2 of 3x minus 2. And the way that they tell us to do that is to estimate the limit numerically. So do the same thing we did before. We know that we're trying to find as x approaches 2, and so we're going to pick values on each side of x. I'll be nice and follow the rules this time. We'll do it horizontally like they do in the book. So 1.9 for x, 1.99, 1.999. We're getting closer and closer to 2, and then we do 2, and then we do 2.001, and we do 2.01, and 2.1. So anyway, those values, 3.7, 3.97, we're just plugging in values in the functions, right? 3.997, it becomes pretty clear that everything's converging on this 4. 4.003, 4.030, and then finally 4.3. So we would say, by estimating it numerically here, that the limit as x approaches 2 of 3x minus 2 would be 4. Now we notice, what happens if I plug in 2 to this equation?
You get 4.
I get 4. So we're gonna write some rules down in a moment. Like if it's an equation where you can just plug the number in and that is the value, then generally that's going to be what the limit is for that function. Okay? But we're proving that numerically by choosing numbers that are smaller and larger than the 2 and just plugging it in our function to see what we get. So here, 3x minus 2 at 2 is defined, right? But what if you have a function like this? The limit, and this is where limits become really more useful to us. The limit of x over square root of x plus 1 minus 1. What if I plug 0 into that function? Huh?
Wouldn't it just be 0?
It'd
Undefined.
be undefined.
It would be
because it's not
undefined. The top would be 0, but the bottom, we get 0 on the bottom. And anytime you have 0 on the bottom of a fraction, it's undefined, right? So we actually can't just plug the value in and determine what that would be. But we can do the same thing with our table. And so what they show us is that as you start plugging in values, and I'm just going to do, we're going to go to each side of 0. So I'm just going to do the ones that are really, really close. 0.0001. Here's 0. And here's 0.0001. And so this is 1.99995, and this is 2.00005. And so it seems pretty clear as we're picking numbers on each side here that they're all converging on this value of 2, right?
So how are we calculating the f of x? Like when we put in -0.0001, how are we getting 1.9? We're just plugging 0.
You're plugging in those values for x here in this function. Right, so if you plug that into your calculator, you're going to get this decimal value. If you plug that into your calculator, you're going to get that decimal value. Okay?
So why do we need to make the table? Is that just like the problem? We're just supposed to make
Well, like I said, we can't. For this one, we really didn't need to. Because we could just plug in 2 and see that clearly the limit as x approaches 2 is 4. Because that function is defined at if x is equal to 2. Right? So here we could have just plugged it in and not done the table, but we can't do that here because if you plug it in, you get if you try to plug in a 0 in your calculator for this function, it's going to be you're going to get an error, right?
How did they get 2?
So we know that it's as x approaches 0. So there's a lot more values in the book. I was just trying to save time and marker by not writing that down, right? But we're trying to get to. We're picking values on each side of 0, right? So we're picking values that they start with -0.01, and then they do -0.001, and then finally -0.0001 for values of x. And then they pick values on the other side of 0, so they do 0.0001, and they do 0.01, and they do 0.001, and they do 0.01. And so it becomes obvious as you're picking values around the 0 there that they're all converging on this point, which is a value of 2. Does that make sense?
So you just like choose the whole number that's in between them? Or can it be
yes. All right. And if you look at the graph of that, like if you were to graph it, this thing has a graph that they show the graph in the book, but it looks like up here 1. So -1, it has a value of 1 right there. Then it goes. Here's our 2, it has a hole right there, it does that, and it keeps going. Right, so that's what the graph looks like. So the graph would sort of prove that as well. It's not defined right there at that point, but that's the limit. So it just highlights the fact that a function may not be defined at a particular value of x, but the limit will still be defined. Because everything is definitely converging on this point here, even though that point's not actually defined for the function. Okay? Welcome to calculus. Right, these are the kind of things you think about in calculus. So like one entire semester, I guess, you guys, yes, semester now. One entire semester of calculus. I don't know how I was on the quarter system, so I don't know how they organize it now, but when I'm in the quarter system, basically one of the calculuses was entirely devoted to limits. Like that's what we spent all of our times on. You did limits and you did derivatives.
It's like the questions they keep people who do calculus up at night. They're like, man, I wonder what the limit of x approaches.
Right, exactly. Yeah, I couldn't sleep at all while I was in college. I was like, I wonder what the limit of this. It's the kind of stuff I thought about all the time. Yeah. All right, let's see if I can read it. Here we go with the backboard. Oh, let's just try one more. Hey, see, that was the good one. I didn't account for the lack of ink in this one. It kind of threw my balance.
Oh yeah.
So everyone gets a point.
Yeah, that's really what that's for. So if I read the trash can, I don't have to deal with.
Yeah, I think we should just do it fine now.
Okay. Does that make sense to everybody though?
I mean, like, I understand how to do the problem.
Right.
But, like, the problem itself.
This is really what we were trying to get to. It's like if I had asked you before, if I said evaluate, if f of x is equal to x over the square root of x plus 1 minus 1, I said evaluate that function at 0, you would say it's undefined. Right? And so that wouldn't really tell us about what's happening around here and if it's convergent on a particular point. But now when we do the limit, we can see that it's convergent on this point. You can tell me what the value, what the limit of that would be. So we still have an idea of what the function is doing, even though there's no point defined when x equals 0. All right. You can use a graphing utility to do the same thing on your calculator. So why don't you pull out your calculator and punch in example 4. And let's see. Let's see if I can do that as well. So I'm going to go to my online calculator here. That won't work. Let's see. Whoa! Can't do that. Justify. Where is it?
I entered into the calculator.
All right. So was everybody able to punch it in?
No.
So you're gonna go to your graph. You're gonna go to y equals.
Did you put parentheses?
Go to y equals. Yeah. Make sure you use parentheses where appropriate. So I'm going to clear, if you want to see how to do it, I'm going to clear mine out. I went to y equals, and I'm going to punch in, I'm going to use parentheses on top. So x, I'm going to use the, whoops, didn't do what.
Wait, what's an example?
Number 4. All right, x, come on. Obviously, I can't use the keyboard like I want to. So I'm going to use the little caret T key to say x squared, or I could use the square thing there.
Wait, you need to do 3 for
That's, but it's cubed, sorry. I have to use the caret key. You guys know what I mean by the caret key? It's
Yes.
a little up,
Yeah.
little house top, right?
You got this, Walker.
I could do this. X cubed. All right, minus, all right, x squared plus x minus 1. And then close your parentheses again, and then divided by, and then x minus 1. So we got to use parentheses again.
Don't forget those parentheses.
That's right, that will totally change the problem if you leave those out. Now I'm going to graph it. All right, there it is. So there's my graph, and we're trying to evaluate this. It's the limit as x approaches 1. Right, so we're trying to see what the value is at x1. So we can use the trace feature to kind of see what that does. So as you go along, as you kind of trace along here, you can see my x values at the bottom there. At 0.85, we're at 1.72. When I go to 1.06, y becomes 2.1. So it looks like they're convergent on 2. Well, we can go to the table and look at it there. So I hit the second function in my graph key over here, which will take me to the table values. And if I go to the table values and go to where 1 is,
It says error.
it says error. I need to set my table set.
Where do you see it? I
Error.
think it's just the way your table's set. I think your table's set. Because mine is all whole numbers. There's just.
You have all
Yeah,
whole
you
numbers.
have to go to, yeah, I have all whole numbers too.
Wait, what does it say all?
Oh, table set?
You have to go
Go to table
setup,
set
and then you're gonna
and
start
pick
one,
a table start.
and then you're just gonna like
It's the change in table that's going to give you the whole numbers.
start at 0.
Right.
Table
So I
start
can
at 0.
do.
Table set.
It's above one now.
And then
I'm going to do like point
actually,
0.8.
I don't know.
I have it for 2.
Oops.
What about the one under that?
I'm going to try
Mine
to
says at 0.
point,
It goes to 1.
Mine was already.
0.8, and then the one underneath it. You want to go. You want to do. Looking at like the values they have in the book, they're going 0.002 is what they're doing. 0.002.
Where do you see that?
I'm just looking at the way that they've got the values in the book. You see how it's like 0.9, no, not 0.002, I'm sorry, I'm looking at the y values. They're doing 0.001. So you do see how it's increasing by 1 each time? By 0.001?
Yeah.
So the x value is 0.997 and then 0.998 and 0.999, right? So really I don't have to do 0.8, I could do something closer because we're just trying to see what it's converging on. So I'll do 0.99, how about
It's
that?
just taking a while to get there.
And then we'll go to table. All right, there we go, 0.999. Let's go down, 991, 99. Oh, I got an error right there.
Sheesh. No.
But it's very clear when you do it like that, when you make it small enough that, you know, it's 1.996, 1.998, we're expecting 2.0 error, then 2.002, 2.004. So clearly the limit as x approaches 1 is going to be 2 for this guy.
Whoa.
Can everybody see that?
Why did it
So
say error?
cool.
Because again, the function's not defined at that point. If you plug in a 1, you get a 0 on the bottom of your fraction for this particular function that's undefined.
Oh.
So
Oh,
instead
I
of
didn't even see that.
making our own graph, could we just use like our own like sectioning it off and trying to
Yeah,
so
so
we
you
just use our
You
graph.
can use the calc. I mean, if I were to ask you explicitly on a problem, I said, give me the numerical values, then you'd want to do something like this
Yeah.
so that I see that, right? But yeah, you can just use your graphing calculator, but you are going to have to know how to adjust the table set and all that kind of stuff so that it'll be, you can see those values, right? So did everybody see what I did? Does anybody need me to go through that one more time as far
No.
as the table set goes?
You go second, you go table set.
Yep, second
And
function,
then
table set.
You do table start and you put in your number and then you go to table 1.
That's right.
How you want it.
So you got to do values again. Why did I choose 0.998 and a change in the table value of 0.001? Because
So you
I'm
can
trying to
see
go
it
on
go.
each side of 1, right? Where our limit is, the limit is as x approaches 1. So I start at some values that are a little bit smaller than 1, and I want it to go to some values that are a little bit bigger than 1, so I can see what's happening right there at 1. Okay? And again, I defined my values when I click y equals x. And that's where I put the function. Don't forget your parentheses because it will be, they don't have parentheses in the book, but you need to make sure that that entire top part is divided by the entire bottom part. So I put parentheses around each of that. Well, they show you on the right side. Well, actually in the numerical solution, they write parentheses about it around it down there so that you see to put those in. All right, questions?
No.
No.
All right, this next one's really weird. To me, this next problem is the weirdest problem in the whole section.
So we won't have a problem on it on our quiz.
So this next problem is really
That's right.
I should have recorded that in the book, actually. I mean, on the video, but I didn't. So, if you're, thankfully everybody's here, but I totally meant to do that. That was my bad. But you know what? Just for the sake of everybody and the sake of the video in the future, I'm going to go through that one more time. All right? And this, that way, if anybody didn't understand it and you didn't want to ask the question, you'll have a chance to see it one more time. All right? So this is all I did. I went to my calculator. I went to y equals. I entered in example 4 with the parentheses around the top and the bottom. Right? I graphed it first. And when I graphed it, it looked like that. I clicked trace. And I could move this along my curve here. And when I got close to x1, around x, at x equals 8.85, it was 1.72. At x equals 1.06, it was 2.1. So it looks like it's converging on 2. But the table set really was what made that very clear. So I went to my, table set, hit second function table set here. That's not right. Second function table set. I told it to start at 0.998, and I said increment by 0.001. Because those are the values, that will give me values that are around the number 1, and then I click second function table, and so then I could see that at 0.998 we had, we were getting closer and closer to 2, we got an error at 1, and then as we got bigger than 1, we were a little bit bigger than 2. So I conclude that the limit of this function as x approaches 1 is 2. Okay?
That's a lot.
All right, so let's go back to, like I said, the weirdest problem in the section. Everybody just got dizzy that was watching the video at home.
I don't get motion.
Yeah.
Okay.
All right, there we go.
Thanks for the little cream.
Okay. So what does example 5 say? Example 5 is one of those piecewise functions. You guys remember those?
Yes.
We had like 2 different functions that defines the function overall. And
Don't remember.
so for the piecewise function, it says that f of x equals 2,
Where x cannot equal 3.
where x doesn't equal 3, and then it equals 0 when x equals 3,
Yes.
right?
Yep.
And so they asked us to find the limit as x approaches 3 of this function.
But x can't be 3.
Okay?
Got it.
Now, if I were to see this problem, and even with what I've learned about limits so far, I would have kind of thought maybe because I can plug in 0 and this function is not, I'm sorry, I did this, yeah, that's right. Because I can plug in 3 and this function has a value at 3, and the value of the function at 3 is 0,
Yes.
then I might assume that the limit as x approaches 3 is also 0. But remember how a limit is defined. A limit is, the way we think about limits is we look at values that are approaching from the left side and we look at values that are approaching from the right side on that number line. And what are they converging on? That tells us what the limit is, right? Well, if you do that, if you think about this function, the top function here is, f of x equals 2. So if we go here, it's just a horizontal line. But when x is equal to 3, right, we've got a hole in that line because it's not defined right there. But if I look at every value on each side of 3, it's clearly approaching a value of 2, right? So even though our piecewise the function is defined at 3, and if we plugged it in directly, we would say the value is 0. The limit of that is actually going to be 2, because that's what the values on each side of 3 are converging towards.
Oh.
Does that make sense to everybody?
No.
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 You got to think about what a limit is.
It makes sense.
A limit is not what is the exact value of the function at that point, because we've seen from several problems we can't even tell you what the exact value is because it's undefined at that point, right?
Yes.
But the definition of a limit is what point are values on each side of that x value converging on, right? So we're looking for the limit as x approaches 3, and if x approaches 3 from this side, all the values are 2, so clearly it's converging on a y value of 2. If I look at x from this side, all the values are 2, so it's converging on a value of 2 for x equals 3. So the limit, what point is it converging on? Well, it's converging on a value of 2.
Okay.
No.
Even though the actual value of the function at
That
x
point.
equals 3 is 0. Okay? We didn't ask for what's the value when x equals 3. We asked for what's the limit as x approaches 3.
Is it 2 because the line's at 2?
Yeah, it's because every other value, like I said, if I pick value on it, if I did my table, if I did my numeric table like I've done before, every value before and after 3 is going to be 2. So we would have to say that the limit then is 2 as well. So you see why this is a weird problem, right?
Yes. But
And it highlights the difference between limits versus actually plugging that value in. Okay? Now it is possible for a limit not to exist.
I like that.
You like that?
No,
Is
it's
that-
not for
oh, that's an
multiple.
option?
No limits.
Every multiple choice problem does not exist. Steve was like, I'm totally choosing it. Does not exist. Does not exist. None of the above. None of the above. And so here's just for the sake of time, I'm going to write down the three conditions in which a limit does not exist. Okay, so they are this. Conditions when limits don't exist. All right, and they are Number one, f of x approaches a different number from the right than the left. All right? So to show you a quick example of that, I should have left the graph there. Suppose you have a function that looks something like this. And we're trying to find the limit of that function as x approaches, we'll say this is 2 right here. Limit as x approaches 2 of f of x. Okay?
Because the limit from the left is 1 and the limit from the right is 2.
It's 2. So if that's the case, if as you approach from each side it's a different number, then there is no limit. Okay?
Makes sense. Makes sense.
The second example is f of x increases or decreases without bound as x approaches c. So like some of those problems where we had a function like this, and as x is approaching 0, then we could even, you might have a function that looks like this, where it's both sides here. And they're kind of both converging, on this line, which is the y-axis. But you're never going to be able to nail that down to a particular y value because it just continues to increase without bound, right? Our function continues to go up. So for those examples there's not going to be a limit. Your limit would be undefined for that, where no limit exists. And then the last one is, I'll just go ahead and write down the example they give in the book. The limit as x approaches 0 of sine of 1 over x. And so that particular function is an example where f of x oscillates between two fixed values as x approaches c. And so if you look at this guy, if you plug in values, and they pick some here where x, this is f of x, x and f of x. If you pick some values and start approaching 0, like as you go 2 over pi for x, and then 2 over 3 pi for x. I'm just picking numbers. If you punch these in, you'd see these are decimals that get closer and closer to 0. 2 over 7 pi, and I just go on and on and on. And so what happens is you start plugging these values in, it goes back and forth between 1 and negative 1, 1 and negative 1. It doesn't matter. As you get closer and closer to 0, it's still going to continue to go 1, negative 1, 1, negative 1. And so they have a graph of that on page 754, and you see how this just got a bunch of lines that are all bunched up there around that 0 point. And this thing's just all day going back and forth, right? So when you have y values that are flipping back and forth like this, then there's just no limit. The limit doesn't exist, all right? So any questions about either of these three conditions where they don't exist?
No.
Anybody besides Adelaide said? That's good? All right, so often a limit can be determined by direct substitution. That's what we did in like that second problem, right? We had, what was it, 3x minus 2. F of x was, f of x equals 3x minus 2. And we said, what's the limit as x approaches 2 of f of x? And all we had to do really was just plug the 2 in and see that 6 minus 2 is 4. So we would say the limit is 4, right? Because the function was defined. So this is what we call direct substitution. We just directly substitute the number in that the c value that x is approaching, right? And so oftentimes we can just find the limit based on that. I'm not going to write all these down, but they give a list of functions at the top of page 75. So the limit as x approaches c of b equals b. So that's where b is just that's like the limit as x approaches 2 of 3. If f of x equals 3, then what is that a graph of? Remember, f of x can just be thought of as y. So it's the same as y equals 3. So that's just a horizontal line that crosses at 3, right? Every value, no matter what value of x you choose, the y value will always be 3. You guys see that? Y equals some constant is a horizontal line. X equals some constant is a vertical line. Okay? And so if you have a function where it's just some constant, then the limit as x approaches any number of a constant function is just going to be whatever the value is of that constant function. You guys see that? If x equals the limit of x of c as x of just the function x is just the value c, we could just plug in c. So we're really just plugging in c for all of those. If you look at those different functions they've got listed there, x to the n, we just plug in c for x, and so c to the n is defined. The one that's a little bit weird is number 4, the limit of x as x approaches c of in the nth root of x equals, you can just plug c in directly, but they have a little note there that says for n even and c greater than 0. So that one you can just plug in and do direct substitution as long as the n is an even value.
Do we have to know all these, like memorize them?
Well, you need to, I'm not concerned about you memorizing these like for the quiz, but I would write them down for the test, right, just so you got that. But really the point of this whole section here is the fact that oftentimes you can just plug in the value for c, right? Remember, c is this value here, what x is approaching. And oftentimes if the function is defined at that value, then almost always you just plug that value in, right? We saw the weird one with the piecewise function that you couldn't just plug it in and do direct substitution. But if it's not some kind of weird graph like that, usually you can just directly substitute in and that will be the limit. You have a question? Okay. Now, like the properties of the limits that are at the bottom of page 755, they're just showing you that you can kind of break up some of these into the individual limits. So you can combine things together. So let's just do an example, and I'll show you what I'm talking about. There's some examples at the top of page 756. So again, this kind of goes along with the direct substitution idea, but the limit as x approaches 4 of x squared, again, we can just directly substitute that in. We can say that that's simply going to be 4 squared, which equals 16. Right? There's no issue with plugging in 4 there. The function's not undefined at that point or anything, so we just plug that value in. The limit of, as x approaches 4 of 5x, you can think of this either way, right? You can either think, well, let's do direct substitution and just plug in the 4 and just say 5 times 4 equals 20. Or, based on those properties that you have at the bottom of page 755, you could say this means this is just a scalar multiple. It's just a constant number that we're multiplying the x by. We could say this is the same thing as 5 times the limit as x approaches 4 of x. And so we can, again, that turns out to be the same thing. It gives you 20. So you can look through those. I don't really think any of those are particularly hard. For each of them, really, you're just directly substituting in. But they're showing you how you can, maybe one that's a little bit weird, just to make sure that we understand this, is the limit as x approaches pi of x times the cosine of x. And so they're showing us, based on those properties of limits, that we can split this up and say that means it's the limit as x approaches pi of x times the limit as x approaches pi of cosine of x. And so the limit as x approaches pi of just x is x, and the cosine of x is, I'm sorry, the cosine of pi. The cosine of pi would be -1. So this is a -1 here. And so our final, I'm sorry, this should have been pi. My bad. So the final value is -pi. So I'm going to make sure I didn't lose anybody there when I did that. It's just showing you if this stuff that's in parentheses here is added together or multiplied together or anything like that, you can break that up into individual limits and do the individual limits and then do the mathematical operation afterwards. Okay? Does everybody understand that the limit of as x approaches pi of x is just pi?
Yes.
And does everybody understand the limit as x approaches pi of cosine of x is -1 because the cosine of pi is -1?
Yes.
Right? So our final value is -pi. The same basic thing for polynomials. This is the last thing. I just want you to see it so that you won't be confused by it when you have to do homework on it. And we'll do, I'm not going to write down the instructions. Again, it's just the whole direct substitution thing. If you can plug x in directly, just plug in x. But the limit of x approaching -1 of x squared plus x minus 6 over x plus 3. This is the last example. As long as plugging in the value in this bottom part's not going to give me 0, then I can just use direct substitution. That's all it's saying, right? So I'm just going to directly plug -1 into all of these.
Even if it's like a decimal, doesn't matter.
Say that again?
So like even if it's a decimal, doesn't matter.
Does this right here?
Well, like if it can't, anything but 0 is fine. So I'm gonna hold
That's right, yeah. As long as it's not an undefined value, then we just plug it in directly and we punch that into our calculator, we get -3. Okay? So when you can use direct substitution, just use direct substitution. What was the one example we saw where I couldn't use direct substitution?
Where was 0 at the bottom?
Where it was undefined at the top and you had to go through.
So 0 at the bottom, I guess there was another example though, that it was defined, but we couldn't just directly substitute it in. It was that piecewise function, right? So don't forget, when you have some sort of weird function like that, remember again, the limit is what's it approaching as you come from each side. But if it's not any kind of weird function, and plugging in x is not going to make it undefined, just directly substitute x in and that would be the limit. Okay? All right, you guys are good to go. Have a good day. You'll have a homework assignment for 11.1, and next week I will hand out the test.
Will
All
we
right?
have a quiz on?
You will have a quiz next week on 11.1. All right?